and decide whether Q is countably infinite or uncountably infinite. So the question is the same as asking, can I arrange the rational numbers, those are fractions, in an infinite list? And it turns out you can. The book is unnecessarily confusing. I wish the book were not unnecessarily confusing here, but they are. So let's make an infinite list of the elements of Q. And I'm only going to do the positive ones. And then when we do our infinite list, we're going to do it the same way that we did for the integers and the even integers. We're just going to put the negative one right after the positive element. So like when we list 1/2, then we'll put -1/2 right after it. And when we list 4/5, we'll put -4/5 right after it. So I only have to worry right now about the positive ones, and then we'll insert the negative ones into the list. So here's how I'm going to do this. We're going to go 1/1, 1/2, 1/3, 1/4, 1/5, 1/6, etc. That's going to be my first row. So those are all my fractions with numerator 1, and then the denominator is going to continue to increase. All right. Second row is going to be all my fractions with numerator 2, and then the denominators continue to increase. So 2/1, 2/2, 2/3, 2/4, 2/5, 2/6, etc. I've got some repeats in here, right? Like for example, 1/1 and 2/2 are the same number, right? Those both reduce to 1. 1/2 and 2/4 are the same number. Those both reduce. That's okay. When we list out these numbers, we'll just say, oh, do I have a repeat? If so, I just won't put it in the list. And this is where the book is confusing, and I wish it weren't. I'm just going to list them, and then we'll deal with repeats when we get to the list. So keep going. We're going to go down to 6. So we'll go 3/1, 4/1, 5/1, and 6/1. So keep going. Make your little handy dandy chart, and I'll fill this in too. This is way easier on a chalkboard. Also, the snaking is going to be terrible, but we'll do it. Okay, and then the 6s. And then we've got dots going down also. Okay, everybody got their list written out? We're good to go? All right, so let's start snaking through here. Let's actually do this in different color, pink. Why not? Because we can. So we're going to snake through, and we're going to go here and there, and then the next diagonal, and then the next diagonal, and then this isn't too bad actually. The next diagonal, and then one more. And then I would need to do the number that I don't have here, so we'll stop at that point. But that's how I'm going to snake through the list. Oh, I'm impressed. That actually worked out pretty well. So that's how I'm going to snake through the list. And I am going to, again, put the negative number after the positive number. And we're going to start with 0 because that's not in my list. So here's my infinite list of all the elements of Q. We're going to start with 0. And then we'll go with 1/1, and then -1/1. So we're just going to put the -1 right after the positive one. That's what we did with the integers. That's what we did with the even integers. No big deal. So then we've got 1/2 and -1/2, right? 2/1 and -2/1. All good so far? All right. 3/1 and -3/1. 2 over 2, and negative 2 over 2. 1 over 3 and negative 1 over 3. Maybe we'll do one more diagonal and then we'll stop because we got the idea. 1 over 4, negative 1 over 4, 2 over 3, negative 2 over 3, 3 over 2, negative 3 over 2, 4 over 1, negative 4 over 1. And then we'll do a dot, dot, dot. You've got the idea. You could do the next two diagonals if you wanted to, but you've got the idea at this point, right? Everybody's got the idea how we're listing these out. The only other thing that we have to do is, this is technically not a list of all the elements of Q because we've got duplicates in here. So let's go ahead and cross out the duplicates in green. So 0, 1 over 1, negative 1 over 1 is fine. 1/2, negative 1/2. 2 over 1, negative 2 over 1, 3 over 1. And then my first duplicate is 2 over 2. So 2 over 2 is a duplicate. With 1 over 1, we would cross that off, and we would cross off negative 2 over 2. That one's also a duplicate. Do I have any other duplicates in this list? I may not have gotten far enough to have any other duplicates. That might be the only duplicate that I have when I list them out this far. Do we see any other duplicates? I'm really asking. I don't think I have any others this far. But you understand what's going on, right? We're just going to cross off the other duplicates. Everybody's good there. That makes sense. Yes, good, happy. Okay, so therefore, here's my infinite list of all the elements of Q. And therefore, that tells me Q is countably infinite. I've listed out all my elements of Q. We're good to go. So Q is countably infinite. And what this also tells me, and you are really not going to like this, but that's okay, that the cardinality of Q is equal to the cardinality of the natural numbers and also equal to the cardinality of the integers. So there are exactly as many fractions as there are integers. There are exactly as many fractions as there are integers. There are also exactly as many fractions as there are natural numbers or positive integers. It's not something that is intuitive, but it's true, and we just proved it with our lovely pink line snaking all the way through this set. Give me a thumbs up. Tell me this makes sense. You can have an infinite list of the elements of Q. Grace, question.
Okay, so are you just, when we cross things out, are we just saying that we could infinitely cross out doubles as we go along?
Yes. So basically what I'm saying at this point is I have a list that has too many elements in it, right? I wouldn't have to cross them out if I didn't want to. I could still leave them and say this is still an infinite list of the elements of Q. But good practice is to just have each element listed once. And so I'm saying I could go through, remove some. I'm still going to have an infinite list. All I'm doing is making it smaller. If I were making it bigger, I would potentially have an issue. That might cause me some problems. But I'm just making this list smaller in order to have good mathematical practice, only list everything once, and therefore I'm fine. Does that make sense? Does that answer your question? Cool. Good. Other questions? Do you believe that there are as many exactly fractions as whole numbers based on the math? Do you like the fact that there are exactly as many fractions as whole numbers? You can say no, and it's fine. It's not intuitive. It seems like there should be way more fractions than whole numbers, but there are exactly the same number. Okay, one more thing, and two more things. I'm sorry, I lied. Two more things. So first of all, combining sets. This is our first one. Combining countable sets. Combining countable sets. So we have a theorem that tells us what happens when we combine countable sets in a couple different ways. I'm combining two theorems here, 13.5 and 13.6. We're not going to prove these. We're just writing them down so you have the results. So my hypotheses are that A and B are countably infinite. So A and B are going to be countably infinite sets. A and B are countably infinite. You can make two more countably infinite sets then. So first of all, the Cartesian product, A cross B, that's ordered pairs, that is countably infinite. And second, A union B is also countably infinite. So we can make two new sets. A cross B is countably infinite. A union B is countably infinite. I can do intersection also, but all I can say is that A intersect B is countable. It might be finite. I can't necessarily say that this set is countably infinite. It could be a finite set. That set gets smaller though. It's not going to get any bigger. So I might get a finite set or I might get an infinite set, but I'm going to get a countable set. All right. Last thing for today, last thing this semester then, is sizes of infinity. And for this, we are delving into math that I don't have an answer for, and mathematicians don't have an answer for either. So here's what we know. The cardinality of the natural numbers is equal to this thing called Aleph naught, right? That was what we had on the last slide. I'm getting better at writing it. Cardinality of that's backwards, though. Did I do that backwards? No, that's right. Cardinality of the natural numbers is Aleph naught. I know that the cardinality of the real numbers is bigger than Aleph naught, correct? We did both of those last time. We're good with both of those. Everybody's good. So here's the question then. Is there a set A where the cardinality of the natural numbers is smaller than the cardinality of A, which is smaller than the cardinality of the real numbers? Is there a set in between sizes? Do we have a set in between sizes for the natural numbers and the real numbers? And the answer is we don't know. We're not sure. There's actually more of an answer than that. If we say yes, then our assumption, this is called the continuum hypothesis. So if we say yes, then the continuum hypothesis is false. If we say no, then what we're saying is the continuum hypothesis is true. Excuse me. So if we say yes, then that in mathematical terms means the continuum hypothesis is false. And if we say no, then the continuum hypothesis is true. That's what we're saying here. It's more complicated than saying we don't know whether the continuum hypothesis is true or false. What we can do is come up with two different systems of mathematics. So system number one has the continuum hypothesis being true. So this is mathematical system number one. It has a name, but I'm not sure what it is on my piece of paper. And system number two has the continuum hypothesis being false. You can prove different things in different systems. So we can say, if I believe that the continuum hypothesis is false, then I can make all of these assumptions and I can get a whole bunch of theorems and I can prove a whole bunch of stuff in math and we can get this totally consistent system of mathematics. If I say the continuum hypothesis is true, then I can get these other assumptions and I can make these other theorems coming from them and we can get a different system of mathematics. So this is one of the places where there's kind of a branching and there's two different systems of mathematics that you can use. Both are what's called internally consistent. So you get different results in each of these systems. It's kind of like when I write down wrong but consistent on your piece of paper with your homework, right? If you kept going with this assumption that you had, which sadly was wrong, but let's say it's not. If you kept going with this assumption that you had, you could get a whole bunch of math out of it, right? If I kept going with a different assumption, I could get a whole bunch of different math out of it. Same thing with the continuum hypothesis. If it's true, we get some results. If it's false, we get some other results. And since we don't know, and actually I'm not sure if we can prove that the continuum hypothesis is true or not, we have to treat both systems as equally valid. That's the bad news. The good news is that virtually every result in an undergraduate mathematics class is going to be true in both systems. So you don't have to decide, and I don't have to decide when I'm teaching class, do I think the continuum hypothesis is true or false? For our purposes, we're going to get the same results in both systems. It's when you get into upper level analysis, like beyond graduate level, and upper level logic, then you have to say which of these systems do I want to be working in. But for us, for the math that we're going to do, the math is the same in both of these. So it doesn't make a difference. Either way is okay. That's just a quick introduction to sizes of infinity and the continuum hypothesis. There's a ton more that you can read about this if you are interested. I am not super well versed in it because the continuum hypothesis is more on the analysis side of things. And as we've established, that is Dr. Brown and not as much me. So she can probably talk more coherently about the continuum hypothesis. That's more her area than my area. But that's a really quick introduction to it. Does that make any sort of sense that you've got a system over here with a bunch of results if we assume the continuum hypothesis is true, and a system over here with a bunch of results if we assume the continuum hypothesis is false? Kinda, sorta, kinda, sorta, kind of ish? Okay, it's totally graduate level math. Like you play with some of this in graduate level, and then it depends on your area of research and whether you keep going after that or not. So guess what? That's the end of new material. We are done with new material. I think there is more about this. I'm just opening my book. Hang on. I think there is more about this in section 13.4. A little bit, cardinality, infinite chain, all that fun stuff. So if you want to do some reading, you can read especially, page 237. The end of section 13.4, the end of chapter 13, talks about the continuum hypothesis. So we've got a little bit of it there. So if you want to do some more reading, you can. You don't have to, but if you want to, you can. Okay, I will send out homework. No more reading assignments. We're done with reading assignments. I will send out homework for you. Homework's due on Monday. I will hopefully get your chapter 12 homework graded quickly-ish and back to you. I don't know, any logistical questions? Anything else on stuff that's coming up? Logistical questions, anything there? Anybody, anything? Alyssa, yeah.
So the final test, that was just chapters 8 through the end, right?
Yes, yep. The test that's coming up on Monday is chapters 8 through 13, and then we skipped 11, I think. So stuff from chapter 8 onward, yes.
And then do you think at the end I could ask you a quick question just off of the homework that's due today?
Yeah, I can stay on. Yep. Other questions? Okay, then last, before we sign off and Alyssa has a homework question, let me just say thank you so very much for A, letting me teach synchronously, and B, coming to class and turning on your video. You have no idea how much easier that made this semester for me. I don't know if it made the semester easier for you or not, but it has been so much easier for me to be able to do this live and not have to be able to create slides or record presentations and have you guys catch my mistakes and answer them live, as opposed to I said something wrong and then you're all confused and we can't straighten it out right away. So thank you, lots and lots. It has been the best possible way to end a really bad semester, and I very much appreciate you letting me teach synchronously. Thank you for that, and thank you for showing up and turning on your video. I really don't want to see you ever again on a computer screen, but it's been really nice to see you on a computer screen for the second half of the semester. Friday whirlwind tour. Last call for questions before most of you sign off. Anybody, anything? Okay, thank you. See you on Friday, and I'll send out homework.